All right, let's dive right into this explainer. Today, we're going to build a rock-solid core intuition around matrix transposing. We're talking the whole shebang, starting from the foundational math theory, moving through how your software actually handles the data, and going all the way down to the bare metal of your GPU. So, if you've ever felt kind of lost when it comes to array manipulations, well, you're in exactly the right place. So here's our roadmap for today. First, why do we even transpose? Then we'll get into the data ribbon intuition, followed by reshape versus transpose. After that, we'll look at PyTorch specifically, transpose or permute. And finally, we'll uncover the hidden performance costs.
Okay, part one. Why do we transpose? Let's talk math and intuition.
So, let's start with a fundamental question that frustrates, honestly, a ton of beginner and even intermediate data scientists. If you've ever felt like just slapping a dot T onto the end of a matrix is some random trick to stop dimension mismatch errors in your code, you're absolutely not alone. We see this talked about all the time on forums like deeplearning.ai and Reddit. People are always asking, wait, am I just doing this to make the compiler happy, or is there a legitimate reason? Well, the crucial point here is that transposing isn't just some arbitrary hack. Not at all. It fundamentally makes two matrices compatible for multiplication by shifting our mathematical perspective. Basically, you're moving from an input space to an output space. It acts like a geometric bridge, making sure that the corresponding elements multiply together exactly how they're supposed to. A really great example of this is how the need to transpose often just comes down to how your data was arranged by convention in the first place. Take Andrew Yang's famous courses, for instance. When he teaches logistic regression, he treats independent weights as column vectors, so you absolutely have to transpose them to multiply with your input features. But later, when he gets into full neural networks, he stacks the weights for each neuron into rows right from the start. And because of that setup, no transpose is needed. The underlying math hasn't changed at all. The transpose is just adapting to whichever data convention you chose. Moving on to part two, the data ribbon intuition. This is all about memory. Now that we have the mathematical why, let's talk about the software how. There's this incredible mental model from the Python Alchemist blog that is just foundational. See, when you create, say, a 3x4 array in Python, it doesn't actually live in your computer's RAM as this nice, neat 2D grid. Nope. It actually exists as one long, continuous ribbon. Think of it like a really long grocery store receipt of 12 numbers. This flat layout is called row major order. So literally every multi-dimensional array you ever create is secretly just a flat line of data under the hood. To really grasp what the software is doing, you have to understand that the actual data values on this ribbon almost never move. Because moving data around, that's slow and it's expensive. Instead, libraries like NumPy just update the metadata. They use what are called strides. Basically, strides are just instructions that tell the program how many steps to jump along that ribbon to find the next value. If you change the strides, you change the shape. But the physical ribbon of data, that stays exactly the same. All right, part three, reshape versus transpose, or folding versus shuffling. Let's see how this ribbon concept highlights the critical difference between reshaping and transposing, because this trips up countless programmers. Notice the stark contrast here. Reshape literally just folds the ribbon. It keeps the exact same reading order, like 1, 2, 3, 4, 5. Transpose, on the other hand, fundamentally changes those stride jumps we just talked about. It totally scrambles the reading order, telling the computer to jump across the ribbon to read column by column. So it reads 15926. Now, both operations are super fast. They happen instantly in big O of one time because they're just updating metadata. But how they interpret that data is completely different. And this core intuition explains a total classic mistake. Have you ever tried to rotate an image matrix using Reshape? If you have, you know you just end up with pixelated garbage on your screen. That's because Reshape just folds the pixels along that exact same reading order. If you actually want to rotate an image, you have to use Transpose to mathematically swap those geometric x and y axes. Which brings us to part 4, PyTorch tools, transpose or permute. So what happens when we jump from simple NumPy arrays to the massive, multidimensional tensors we use in modern deep learning? Well, if you're in PyTorch, you basically have two tools. Transpose is your simple, precise tool. It only lets you swap exactly 2 dimensions at a time. But permute? Permute is the flexible big sibling. It lets you completely reorder complex multidimensional data all in one single go. Imagine a batch of images. You've got batch size, color channels, height, and width. Permute lets you shuffle all 4 of those axes into any order you want simultaneously. So the takeaway here, if you're doing simple, efficient computations with just 2 axes, like your standard matrix multiplication, stick to transpose. But if your neural network needs you to juggle batch sizes, spatial dimensions, and RGB color channels all at the same time before feeding them into, say, a convolutional layer, yeah, permute is absolutely the way to go for sure. Finally, Part 5, the hidden performance cost. Let's look at the hardware realities. This brings us to the most surprising part of our explainer. We just established that transpose only changes how we read the ribbon without actually moving the data in memory, right? So, does it actually cost us anything in performance when we run this on the bare metal of a GPU? To answer that, there's this fascinating archive paper that analyzed the cuBLAS library, which, if you don't know, is basically the engine powering deep learning on NVIDIA GPUs. The researchers broke things down into standard NN operations, meaning no transpose, and NT operations, where one matrix is transposed during the multiplication. And wow, look at the massive spikes on this chart. This reveals a totally unexpected hardware reality. In about 20% of cases on a GTX 1080, standard no transpose matrix multiplication is faster than transpose multiplication, sometimes by a factor of 2 or more. It's crazy. So wait, why does this even happen if we're technically just updating metadata? Well, the GPU struggles with these transpose operations because jumping wildly all over that memory ribbon completely ruins what's called memory coalescing. Hardware really likes to fetch data in nice continuous chunks. When a transpose forces the GPU to read scattered addresses all over the place, it creates massive traffic jams in shared memory. On top of that, to save space, these libraries often use really sluggish in-place algorithms to handle the transpose, which bogs things down even more. But here is the cool part. The researchers proved that you can actually speed up your neural network training just by being a bit deliberate. They proposed what they call the TNN method. The idea is, instead of forcing the multiplier to handle a messy transpose on the fly, you manually allocate extra memory, perform a clean, out-of-place matrix transpose first, and then run your standard, blazing fast NN multiplication. Honestly, sometimes doing it in 2 dedicated steps like that is just flat out faster. Now, because the fastest method really depends on the exact shape and size of your specific matrices, the researchers went a step further and built a machine learning model called MTNN. It uses a decision tree to automatically predict on the fly whether the standard method or their new 2-step method is going to be faster. They integrated this into the Caffe deep learning framework, and it sped up overall training by an average of 28%. Some specific operations even improved by 54%, which is just huge. So let's wrap this up with a final thought for you. The next time you're coding and you just toss in a .t or a reshape to fix some quick shape error, stop and ask yourself, are you just harmlessly folding the mathematical ribbon, or are you secretly tanking your GPU's memory bandwidth? Truly understanding this bridge between the math, the memory, and the metal is what separates good coders from truly great engineers. Thanks for joining me for this explainer, and definitely keep questioning what's happening under the hood.